Professor, you are muted.
Thank you. Okay. Sorry about that. All right. Yeah, we're going to get started pretty quick here, and but just a couple of administrative things to start with. Course evaluations. I've seen a few of y'all have started those. Of course, I don't know who or whatever. I just get numbers from the registrar. So please complete those course evaluations as you can. And I will be traveling tomorrow and without my computer. I don't think I'm taking my computer with me, so not very available, but I will be available on Thursday, and I've added some office hours on Friday also. So please get with me if you're struggling to wrap up the semester in this course. I've went through and graded the CDMA spread spectrum assignment, and so I'm now next going to be going back and grading all the late submissions. So please be getting those in. I'm going to go back to the very beginning and work my way through. Obviously, I'm taking points off for as we've gone along, I've taken off for like a quarter point or a half point or so if you've just been a day or two late. If you've been much more late than that, then taking off a little bit more. I'm going to continue that trend. So please get things in as quickly as possible. And I do need to cut things off at a certain point. So I expect every assignment to be in by Friday afternoon. Please message me or meet me in office hours, make an appointment with me if there's any issues with that. Again, we'll have the self-evaluation, self-assessment coming up later in the week. And on Friday, we'll have a semester review. The final is next Thursday. I think everyone should be on board with that. No one so far has contacted me with any conflicts on, for example, having 3 finals on one day or, that type of thing. So I'm assuming that everyone's good to be taking the final in class on next a week from Thursday. So, all right, let's get going. So one of the things that the department is doing is trying to enhance our machine learning experiences. Obviously, it's a very important technical topic these days. Actually, it goes way beyond technical type issues. And I think there's a goal to eventually have a concentration in machine learning. So we have added some a lecture on machine learning here in this course. So that's going to be today. I have copied a bunch of slides from other courses into this, and there's way more slides than I'll get through today. But I think it'll still be useful for you to look through and kind of understand. There's going to probably be some appearance of this material on the final, but I will not expect you to understand the slides that I don't address during this lecture. So one other thing, you should all have seen the notice, but just in case it got buried in your email, there is a lecture online that is taking the place of the class session we had canceled, I think back in late January or early February, something like that. And it's on standards and current research trends. I expect to be asked a question, some sort of question on standards on the final exam, so you should be aware of that. I think last year I kind of probed the knowledge about the IEEE standards process and procedures. So kind of emphasize that. All right, so we'll start with machine learning concepts. Oh, and so that's on my YouTube channel, and you should all be able to find that. There's a link on Moodle at the beginning. It's links to my playlist, and that should be one of the last in that playlist. So if you have trouble finding it, I think it's labeled lecture 24, 25. Just make sure you're looking at the 2024 version and not the 2023 version, because I think they're all on the same playlist. All right, so back to this lecture, machine learning concepts. We'll look at neural networks, a few different kinds, and then we'll touch on just a few selected applications in wireless communications. So let's start with some concepts. First, when we look at artificial intelligence and machine learning in particular, we have three different learning styles. There's supervised learning, in which we kind of have the questions and answers, right? And we teach an algorithm to produce the expected results when given the set of inputs, right? So we've got a set of questions, inputs, and a set of answers or results, or in the industry we call them labels, right? And so we iteratively, very large data sets, and we teach the system how to produce those results, right? Then we have also unsupervised learning. This uses lots of data, but it doesn't have answers, specific answers a priori or in advance, right? But what it can do is it can find trends, it can cluster data, that type of thing. So, it's useful. It's easier to gather data because you don't have to label all that data, and labeling the data in some domains can end up being the most costly part of a machine learning exercise. And then finally, we have reinforcement learning. And this is a type of system where you use many trials or experiences, perhaps in a simulator, maybe in real life, to explore how to best solve a problem. So you can think of it as trial and error. So you make some trials, you make some attempts, you look at your results, how did they work out? You do it again with maybe some different attempts at it, and you start comparing results, and you keep the best results and the approach that led to the best results. All right, so let's look at supervised learning in a little bit more detail. Here we have a data set with lots of different inputs and correct outputs, right? And hopefully they're correct, right? And so part of your process is gathering this data set, making sure that the labels or the outputs are as correct as possible. And then you adjust this model, right? So the model has trainable parameters, and you will supply some inputs to it, and it will, whatever the parameters are set at the moment, will produce some sort of prediction or forward prediction or answers, right? And then we compare that forward predictions with what we expect, right? What we know the answers to be, right? Again, it's supervised learning. So we know the answers in this training data set. We compare those and we look at the differences, and we move backwards now through this model and update our parameters, so that then on the next iteration, when we do these forward predictions, they're better matched to the answers we know are supposed to happen. So there's an iteration going on here, and we're minimizing the difference between these forward predictions and the correct outputs we know we're supposed to get. All right, so let's look at neural networks, which is a particular way to implement a machine learning algorithm, and particularly useful in supervised learning. We use it in some of those other approaches also. So a neural network has a set of weights, and these control how much influence each input has on a particular neuron, right? So this is a neural network, so it's composed of a bunch of neurons. And So we might have multiple inputs to this neuron, and then we might also have some kind of fixed bias term, and that can add an offset to kind of the weighted sum of these inputs. And then we're going to have a nonlinear activation function that these inputs and processed inputs are going to go through this activation function. And so that's kind of that neuron. And then we have a whole set of them arranged in some sort of structure. And we train this typically through back propagation. It's kind of the key innovation back in, I think, the late 80s or mid 80s or whatever, that kind of helped neural networks really work. And that's where we adjust those weights and biases to match the results that the training set says you should have. Right. So this is a diagram of a neuron. So we have these inputs here. We've got three inputs: X1, X2, X3. Those could be, in an image recognition type situation, you might have a million or of these, right? So you might have 1,000 by 1,000 pixels in a camera, right? And that would provide a million different inputs, each representing the value of one pixel, right? And then, but in this case, I've shown three, right? So then we multiply this, we form up a vector of these, and we multiply this those by this weighting vector. There's a little transpose operation there just by convention to make sure the multiplication works out. So when this the weighting vector is multiplied by the input vector, you get a scalar, right? And then that's added to the bias term. Then we go through this sigma process. That's an activation function, and we have an output A, right? So that's the whole neuron. Then we organize these neurons into a bunch of layers, right? So we might have an input layer, and then we might have one or more hidden layers, right? So then each of these layers has some number of neurons in it, and they accept inputs from the previous layer, right? And then weight those inputs, add a bias term, go through the activation function, and provide its outputs to the neurons in the next layer. So typically, most basic neural networks are arranged in these layers. And you have an input layer, an output layer, and I've kind of drawn this input layer crudely, but it would be doing this kind of neuron process also. Right. And so then you're going to provide these outputs through this output layer. The hidden layer just means that it has no representation in the training data set, right? So there's a lot of degrees of freedom here for the network to adjust all these weights and biases to ultimately produce the results you want. And this output can take a number of different forms. It could be just like a binary or probabilistic or all sorts of different forms. But this is the overall concept we're dealing with here. And a few notes about activation functions. I'm going to skip a few slides here because it's just getting down too far in the weeds and we don't have time for it. But it needs to be nonlinear. If it's linear, then the layers could all be kind of squished and combined together in even with a very, very deep network, which meaning we have lots of hidden layers, and it could all be collapsed into a single layer, and you kind of lose all that richness of the ability to perform these complex computations, right? So for binary classification, we typically want it to reflect the probability of the result but map that to either a 0 or a 1, right? Or a false or true, or whatever your mapping ends up being. Now the training requires a derivative because we need the slope of the functions that these neurons are providing. So when we have this activation function, it needs to be nonlinear, but we still need to be able to easily calculate the derivative of it. right? So here's an example where here we might have the input Z. Again, this is that weighted combination of weights and of the inputs and the bias term. And you see it's very nonlinear, right? It has this a crazy curve in it. Here's another one, tan H function. ReLU is a very, very popular one these days. Very easy to calculate. It's kind of a piecewise linear type thing, but it's still nonlinear, right? And that has maybe some issues. And so sometimes we add a tiny bit of slope over here, whereas in this pure ReLU, that's any input below 0 produces an output of 0. And but when we have this leaky ReLU, we add a tiny bit of a slope in this region also, and it just helps a little bit. So again, for training, for supervised learning, we start with the data set with inputs and the answers or the labeled results. So we train a neural net to produce the correct results when presented with the inputs, requires adjusting the weights and biases. And here's a very, very popular approach on implementing that, and that's gradient descent. Basically calculates the derivatives of each layer and applies. Oh, I keep forgetting to actually finish that sentence there. I see that every time I lecture using this slide, and I forget to update it. But basically, we're going to calculate this loss function. I'm just going to toss it down here, right? So where y is the expected outputs and y hat are the estimated outputs, right? And then we can actually take the derivative of this, and so we can have this derivative of the loss function with respect to the output, and it's that. And then that's for an individual neuron, but then we can sum them all up together over layers and we call that the cost function represented by the J there, and it's just summation of that loss function. So quick view of gradient descent. You've got this cost function that's a function of some W, right? Weights, biases. This is usually I've drawn it as a kind of one-dimensional or scalar value function, but in general, W's could be thousands of parameters that you're optimizing over, right? But when we just assume this one, we can draw this kind of function here, and we see that we can calculate the slope at any given location, and if this is our lowest cost, right? So that would be the optimum. It means we're matching the outputs the best we possibly can. Then if we're on this side, we're going to calculate slope and kind of move iteratively this direction. If we end up on this side, we'll move this direction. So that's why we need to calculate that derivative, so we can look at that slope and then move this W in the direction of decreasing cost, right? So and then this gets updated, so there's an update equation, and then you repeat the process and trying to get it to converge. There's a little weighting function out here we call the learning rate. So this would be like the old previous weights and the previous biases, and these would be that adjustment that we just calculated. And then instead of trying to go from here right to there, if we just calculate the slope here and we try to get here, we would actually kind of end up down here, right? So we wouldn't exactly get where we wanted to get. So what we do is we step towards there using this learning rate. So we take the existing values and we adjust them by some fraction of what is essentially the error part, right? And if we have too big of learning rate, the steps may overshoot and we'll have convergent problems. If it's too small and we take too many tiny little steps, it's going to take forever to converge, right? So here's the back propagation. I think we've already talked about that. We've got a bunch of hyperparameters like that learning rate. How do you set that? There's a bunch of other things when you get into it. The number of neurons in each hidden layer, the number of hidden layers you have. These are all called hyperparameters, right? So the parameters of the model are your weights and biases, but then there's still lots kind of or at the meta level or hyper layer that we can adjust to try to make this training process better. And there's some tools that kind of help you with that. All right, a key thing we need to be aware of when we're training neural nets is the challenge of generalization versus memorization, right? So if you, for example, as you're studying for finals, if you just memorize all the answers to all the exercises and stuff you performed during a course, you might be able to reproduce that really well, those results really well. But then the professor gives you a little bit different question that is really trying to probe your understanding and knowledge of the topic, but you never really saw that exact question before, right? So if you've only memorized, you may not do very well, right? You'll probably do pretty poorly on that final exam. But if you kind of generalize your knowledge, then yeah, you can do much better on those kind of new questions. So that's what we're talking about. If we overfit a model to our training data, then we're essentially memorizing. So what we want is sufficiently diverse and plentiful data relative to the model complexity, right? So there's a lot of research that goes on exactly what all the rules of thumb should be, and things change and that type of thing. So be careful as you study this area that maybe some of the rules of thumb from the past may not be quite as widely accepted as it is now. But this is the big deal, is to make sure that you're providing good enough, rich enough data so that it can train in a generalized way versus memorization. All right, now we deal with signals in this course, right? So that is kind of a time-based thing. So if we go back here and we look at a neural network, you see that there's no real aspect of time here. You present your inputs, oh, there's some calculations going on, but boom, you get an output, right? And if your inputs change, then the outputs change, but there's no memory involved here, right? So if I apply one set of inputs at one instant, and then I apply another set of inputs a few moments later, that first set of inputs has no bearing at all on the subsequent calculation, right? So that's here's another drawing just with a couple of more hidden layers, right? So that's a problem, right? Because in signals or in the sentences and natural language and a lot of different areas, we're dealing with a sequence of data points, right, that are spread out in time. And a signal, it makes a big difference on what happened before, what's going to happen later, right? Because we put all that signal together, and that's our result, right? So there's signals are a function of time, right? So we can maybe try to handle this with a little bit of memory, and then for this neural network, we could provide not only the current inputs, but maybe the previous inputs, and maybe even the ones previous to that. Here I'm using kind of the Z transform digital control systems kind of perspective, where Z to the -1 is basically a period of T in a sample data type system, right? So so we would have the present inputs, the previous inputs, and the ones previous to that, right? But you can see, boy, if you tried to keep extending this is going to get really messy, and you're going to have a multiplication of the input width here. And so you're going to have lots more input neurons, and your hidden layers are going to have to be very large also. So it's not really very scalable of an approach. So this is, the topic of sequence modeling, right? So how can we process information in time steps or a sequence where information is ordered, right? That's the key. It's time ordered. The memory length determines how far apart in time relationships, in time that relationships can operate, right? So let me say that again. The memory length, right? So how many of these memories that we have determines how far apart in time the relationships can operate. So if we have a sentence, right, in English language, then we have a subject, a verb, a predicate, there's nouns, there's conjunctives, there's all sorts of, I'm not an English professor, right? So forgive me. But you need to make sense out of that sentence, you need to be able to relate that predicate to the subject and vice versa. And you might organize these things into a paragraph. And so you've got your kind of thesis sentence or topic sentence of your paragraph, and you've got a few supporting sentences, and maybe you've got a summary in that paragraph, right? So there's perhaps you need a very long memory length to be able to handle all the relationships of those. So when we look at sequence modeling, we can look at it as having many inputs to one output, right? So that could be a sentiment analysis, right? So we might take someone's online review from an e-commerce site or something like Yelp or whatever, and then kind of provide maybe a number of stars, right? So that would be one output, but scaled in 1 star to 5 stars, right? So that would be one output that's dimensioned in 1 to 5, but it might have many inputs in all the different letters, spaces, characters, words, and that make up the sentence that someone left as a review. Then you could also have a one-to-many type of relationship where you might have an image. Okay, well, maybe technically an image has, a million pixels to it that all have some RGB version. So maybe there's 3 million pixels, but it's still just like one input in time, right? And then that's going to produce a caption of natural language. And let's say it's in English, and it would describe the image, right? So that would be a one-to-many image captioning as an example of that. And then we have many-to-many. And if you traveled much, use Google Translate. And, if I go to France for the Olympics this summer, maybe my French isn't that good, so I'm going to type in my English phrase that I want, right? So that's many characters, many words, and then that's going to produce the characters and words in French, right? So English to French as English as a language translation as an example, and many to many. All right, so now how do we do that? Well, one way of doing it is to have kind of a set of neural networks, and we have here and then set of inputs x0 at time 0, and that's going to produce a y caret or y hat 0, right? So our best estimate of what the output should be at that time. But then we're also going to send some information to another neural network that then takes in x1, and y hat 1 is a function of x1 and this h0, right? And then so on, right? And so we can kind of keep cascading these, right? Where this h is essentially a memory, right? So at any given stage, x1 here, y1, stage 1, we're going to be bringing in this h0. And so perhaps now is a good time to say that these outputs really are functions of the inputs. And in particular, these are nonlinear functions. So neural networks do a great job at approximating nonlinear functions, right? So just think of that in general. The more complex nonlinear of a function you have, the bigger neural net you have, but that's really a great way of implementing or calculating a nonlinear function. All right, so now we had all those kind of in cascade type of relationship, but let's use some feedback, right? And now we've introduced the recurrent neural network. So here we're going to wrap this memory around to the input and be able to still calculate this type of relationship, right? And so here we're doing recursion. Maybe if you've taken a few computer science courses, you've done some advanced programming, maybe you've run into calling a subroutine from itself, right? And it keeps calling itself, calling itself, calling itself. And so that's an example of recursion in software. Here we're doing that. Well, this is probably implemented in software, but we're doing this in this neural network, right? So there's these things end up having a state, right? So when we talk about a stateful versus a stateless system, we're talking about whether it has memory or no memory, right? You may have run into this in embedded systems because we often implement embedded systems using a state machine. Remember studying Moore and Mealy type state machines, right? And so these are essentially this same as this, but now we have done this using a recursion or feedback type of approach. All right, so now how do we train these, right? So training of recurrent neural networks is similar to conventional neural networks in that we use backpropagation, but we do that through time, right? And all right, so by now you're probably if you haven't seen any artificial intelligence or machine learning stuff before in any of your other previous classes or independent work, you might be overwhelmed at this point. Don't worry about too much. I'm just trying to give you the high level type of things here, right? So, but we're getting into more of a subtle issue at this point with the vanishing gradient problem. And remember that when we talked about backpropagation, we're using this gradient descent thing where it's looking at the slope of this cost function, which is comparing, kind of summing up and comparing the ideal versus the actuals results, right? And but when we kind of propagate that back through a number of different layers or through iterations in time, our derivatives can go to zero. Maybe sometimes they explode and go towards infinity, but it gets really, really difficult to, in a deep neural network, go from the end of the network back of, maybe a dozen layers to the beginning, right? And that gets numerically very difficult because our gradients tend to go towards zero. Same thing happens in these recurrent systems. Is after a few iterations, the gradients can vanish, and this can be particularly severe and leads to biasing the short-term effects, right? So you might get a result where the again, go back to the natural language situation, that you would favor the relationships between adjacent letters or words, but really kind of forget any sort of relationships throughout the sentence, right? From that predicate towards the subject or vice versa. So, all right, so some of this is legacy here. We didn't study this last week. We just studied it a few slides ago, right? So, but we're going to rely on the ReLU and that's at kind of 0 when it's less than 0, and then linear, so it's a rectified linear unit when it's linear above 0, right? And that's because it's trivial to calculate the derivative. The derivative's either 0, where it's flat, or it's 1, or some constant where it's greater, where the input's greater than 0, right? And we might use some special initialization techniques for the weights and biases. You got to start somewhere, right? So it's iterative update of these weights and biases. And so we can work at trying to initialize these things really well. So, we're trying to deal with this vanishing gradient problem. But there's some other approaches we can use. And we use this concept of gate. And this gated RNN can control when information flows through a system. And there's this concept of forget, store, update, output. Don't worry about this. I'm just throwing this information out to you, but it looks something like this, right? So it's a more complex type of cell. And so there's some of these activation functions here, and different parts of this can be trained to memorize or forget or update, and then ultimately output the results, right? So there's more recently, there's been a very, very important innovation. This paper, Attention is All You Need, down here, if you're going to read anything on deep learning or kind of the current trends in generative AI and that type of thing. This is a very, very important paper. So it kind of launched a revolution in the sequence modeling, and these large language models that we hear so much about on the news. These rely on this technology typically. It's a combination of several key things, right? So I'm going to well, maybe I've got a little bit of time to go through this. So attention is used to focus processing on certain parts of an image, sequence, blah, 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 right? Based upon similarity between query and keys, and then use that to retrieve or extract a value. We use a dot product, right? So if you think back to when you learn about vectors, vector calculus, that type of thing, you learn a dot product, right? And you take, let's say, 2 vectors, and it tells you how similar they are, right? And how one, if you do it right, dot product can show how a vector projects upon another vector, right? So it's a similarity measurement, right? And so attention uses the scaled dot product of vectors or matrices. And then we have a special layer. Now, I just kind of breeze through the layers that we have, right? So I talked about how neural network has an input layer, some number of hidden layers, and an output layer. Those are all, the diagrams we looked at were fully connected, and that each neuron connects to all the neurons in front of it in the next layer, and accept inputs from all the neurons from the previous layer, right? But we have a bunch of other different types of layers. We've got convolutional layers. We've got kind of dropout layers and max pooling layers. I'm just throwing some names out at you. This softmax layer is an important one here in this case, right? So it's an important activation type that converts classification data into proper probabilities, right? So here, the important thing is that we're going to have maybe multiple outputs, right? But they're all going to be a proper probability. In other words, that each individual output is a measure of the probability that it is the correct one, and that they all, if you add them all up, they add up to 1, right? So think back to what we know about probability theory. Yes, all the different options in that sample space would have a a value greater than or equal to 0 and less than or equal to 1. But when you add them all up, the sum has to equal 1. Right? So that's what that is doing. So here, this is what's called an attention head, and we're doing some matrix multiplications here and some scaling to do this scale dot product for similarities. So we've got these Q's and K's, and then we've got this softmax layer, and then that gets multiplied by this V input also. So our attention looks like this function of these three variables. Of course, these can be multi-dimensional. And then this is the kind of scaling and a dot product operation that's going on. So this dk is the size of the embedding. All right, so I know I haven't given you background material to really understand all this terminology and that type of thing. But hey, if you're an interview, you can tell the interviewer that, yeah, I've studied attention heads, and I've even studied multi-attention heads, multi-head attention mechanisms here, right? So we can take this kind of structure and then kind of expand it in these different dimensions and that type of thing. So, all right, so then this would be the whole transformer model, right? So here we've got multi-head attention. So we built this up from neurons to, you know, an attention head, and then now we've got multi-attention heads, and now we're putting it together in this kind of crazy transformer model. So now you can say that you studied attention models. So all right, so let's look at another topic, right? So I'm going to skip over non-supervised learning or unsupervised learning. What we talked about was all supervised learning. Now we're going to look at reinforcement learning. And again, remember I said that was kind of like a trial and error type of thing, right? So here we're going to have this agent, and this is the guy that's gal that's trying to think and make decisions, right? And so it's going to make decision about conducting some action within an environment. And then when that agent acts within that environment, the state of that environment is going to likely change, right? And so the state changes as an update, and the reward changes also, right? So this agent is actually acting in order to maximize its reward. Right, and kind of a way to think about this is think about a mouse in a maze, and there's a thing of cheese at the other end of the maze, right? So it's trying to make a decision: do I go forward, turn left, turn right? Do I have to back up? What do I need to do to get to that reward, right? So it's making these decisions, right? And so at each iteration here, we evaluate what reward did I get last time out of that action, and what state did I put that into, right? So our inputs into this decision-making process are the current state and the reward that I've gotten in getting to that state, right? So I might be a few turns closer to the cheese, and I can maybe start to smell it, and it smells delicious, right? So I'm getting closer to my ultimate reward, but I'm getting a little reward along the way, right? So the previous slide, really the slide itself describes a single move game, right? So the agent looks at the state, the reward, makes a decision, acts upon that decision. Boom, that's a single move game. We get a new reward. We're in a new state. But, you know, the more general cases, we need to make a series of decisions in order to reach an ultimate goal, right? The mouse has, the ultimate goal is getting to the output of the maze where the cheese is, and you eat the cheese and be all happy. So, but it's got to make a series of decisions in order to get there, right? So a Markov decision process, or MDP, helps us model this scenario by formalizing this sequential decision making, right? So, what time is it? I think I got time. I know I'm rushing really fast here, but assume a discrete set of states, actions, and rewards at discrete times. So everything's kind of discrete in time and discrete in some discrete number or set of states and actions and rewards that are involved in this game or this process. At time step t, the agent receives a representation of the environment state. Right, so that environment is telling the agent, or the agent's got some sensors, it has some perception functions or whatever, and it examines the state. And the agent then selects an action to take based upon the information it has. And so we track this as a state action pair. So we get a state, and then we choose an action based upon that state. Then time is incremented. Now we're in time t+1, and the environment transitions to a new state based on that previous state and the action, right? Think of your state diagrams that you did in digital systems or embedded systems or whatever, right? And you had that state transition diagram. Or think about how we talked about the trellises and the state diagrams earlier in the semester, right? So, so we transition to a new state, and that has been due to the action A of T. And, in real life, there might be some unmodeled external and random effects that maybe we don't always go to the state we thought we were going to get to when we were in this ST, AT, and we think we're going to end up in ST+1, but there might be some possibilities we end up in some other state, right? So, but the agent receives a reward at RT+1, and based upon the new state of the environment, which was in part caused by the selected action, right? Hopefully predominantly by the selected action, right? So we have this new reward that's a function of the previous state and the action taken, right? So we not only entered a new state, but we also received some reward for that. Maybe that's a positive reward, maybe it's a penalty, a negative reward, but we get some reward for that. Note that the same action might have different results in different states. That's why this reward is a function of both the previous state and the action taken based upon that state. And also note the implication that there may be unmodeled external and random effects that affects the next state of the environment, right? So we don't always go where we think we're going. All right, so the state that the environment will enter and the reward that the agent will receive are both random variables. Well, it would be nice if the world was all deterministic, and then our life would be easy, but it's not, so it's hard, and we get paid more money, right? So you tend to get paid more money to solve hard problems than easy problems, right? So I think that's a good thing. The sets of S, the states and rewards, are finite, so we can define the probability of the transition to state S prime, or +1 or whatever, right? The next state with reward R from taking action A in state S. Yeah, I forgot the E there, right? That should be state S, right? So we're in state S. We take action A that produces a reward and a transition to S, right? So we can write this as a conditional probability. Given that we're in state S and we take action A, what's a probability that we get reward R and we transition to state S prime, right? So we can write that out in longhand or shorthand here. So now consider the time sequence, right? 0, 1, 2, 3, ... right? So we might start in state 0, we take action 0, we get reward 1, and we transition to state 1. Then we take action 1, and we get reward 2 and transition to state 2, and so on, right? So this is a mathematical representation of the previous diagram on, well, it's no longer slide 3, but the previous slide. The reward the agent attempts to receive and maximize has been defined for each time step in the sequence. So our question is, what is the best way to maximize reward over the sequence, right? So we have, here we've got our mouse and we've got our cheese and some walls here in this maze, right? So we generally want to maximize the total expected return, right? So we might get a return or reward for each step, but what we're really interested in is the ultimate reward. And we can write that as this sum, a discounted sum of these rewards. So we do this in a stepwise manner. To overemphasize the goal state reward might conflict with some of the steps to get there, right? So if the cheese is there and the mouse is there, he might want to just go directly to it, right? But he's going to run into these walls, right? So if you overemphasize that, he might never get out of this square right here. So what he needs to do is kind of go up here and over there, or maybe around here. Both those are solutions. One probably has a better reward than another. Okay, so actually you could take all sorts of steps here. You might step backwards and all, but you know, what we're interested in is kind of optimizing that reward at overall, right? So we have this reward at each time step, but then we kind of discount them, right? So some sequences are finite, like the mouse and cheese game. If there's a final step, then the sequence from time equals 0 to some capital T is called an episode, and that the system is episodic. Others are continuing and never end. In other words, this cap T here is really infinity, right? So, or nearly infinity, right? So, so we need to really work with this discounted return here, right? So if this gamma is less than 1, right? So that means that we're kind of favoring this T plus 1, but we still include a little bit of reward, T plus 2, T plus 3, and so on. But every time we raise a number less than 1 to a power, and that power is higher and higher, the value gets smaller and smaller, right? So if we take 0.5 here, and then this is going to be 0.25. Right, so it's smaller than this. So this means that this infinite series, even though it goes on to infinity, but each of these terms gets smaller and smaller, and it actually converges. Right, so we adjust this gamma to determine how much to favor the kind of long-term reward versus the short-term reward. Right. But we need a balance there somewhere in between. All right, super quick. I know that's a whole semester of machine learning in a few minutes. So let's look at a few of the examples. Now, dynamic spectrum access is kind of one of the early examples of using machine learning in radio systems, and we kind of started with, you know, in the old days, radios were all hardware, right? And then we started, especially with digital communications, we started doing more and more of that in software. And so we ended up with radios that we would call software-defined radios, where, let's say, much of that decoding, encoding, and constellation formation, all that type of thing is all done in software instead of hardware, right? And then now once we've done some software on it, well, we can maybe add some sort of machine learning or intelligence, add a brain to this radio, so that in software, so that we can teach it to make decisions on its own and just kind of switch over to some different settings in that software, or maybe call some different subroutines or whatever, and it can adapt itself, right? So that we term that cognitive radio. There's a lot of debate on terminology in this field, but since the kind of early 2000s, we've been talking about adding this, right? And dynamic spectrum access was one of the first applications of this idea of making these radios kind of intelligent, right? So most, as we talked about before, most spectrum is allocated to a license holder who has exclusive rights to it over some geographic region, right? And I'm being very vague on how that geographic region is defined. But some primary users need lots of spectrum sometimes, but most of the time only use a small portion of it. One example of that would be public safety, right? So normally they're just, going about doing their little patrols or whatever. But, there's some big, huge fire or mass casualty event or whatever. Boy, you're sending police, firemen, ambulances, other emergency response people. So they all need to communicate with each other, and suddenly the spectrum is jammed, right? So they tend to get enough spectrum to handle the worst case situation, right? But most of the time that spectrum is laying fallow. It's not being used, right? So can secondary users use this spectrum when the primary user is not? Okay, so I'm going to take primary users, I'm going to call those PUs, and secondary users, call those SUs. Can an SU transmit in such a way to not cause harmful interference to a primary user, but still be able to communicate with its receivers, right? So here I'm kind of broadly describing two different modes. This would be opportunistic use of some unused spectrum. And here, this is more of trying to creatively use that spectrum, but in such a way that we're not causing harmful interference. Think about what spread spectrum allows us to do. It allows us to have this kind of multiple access. If go back to CDMA, and one user might be using one code, another user might be using another code. And yes, there's some level of interference, but it's pretty minimal. Right, so these are two broad different concepts on approaching that, right? So now these can potentially be implemented using these cognitive radios that can make complex spectrum decisions and decide on other parameters too in that radio waveform, and without human intervention, right? So it can do it on a very fast time scales. Normally, like license decisions, these take months and years to do, and lawyers get involved, and you have to put things out for public comment sometimes. And so we're radically changing that to be able to make these decisions on millisecond timescales. So reinforcement techniques. So we just looked at reinforcement learning, right? So we can learn the behavior of these primary users, making the sensing process a little bit easier and less error prone, right? So here what we do is we would normally like listen and see if the primary user is using that spectrum. If they're not, okay, we can use it. We're not harming them because they're not using the spectrum, right? But then we have to continue to sense them, and when the primary user does go active, we've got to vacate that spectrum, maybe move to another channel or something like that, right? And but this sensing process is extraordinarily hard, right? So, but if there's some kind of behavior of the primary user that we can learn, then maybe we can get better at it, right? So there's a couple of some challenges with that, right? So regulatory agencies, industries, and advocacy groups are implementing this automated frequency coordination. So sensing's really hard, and it's maybe what we would like to do to be able to make that decision really quick, but we haven't really gotten the technology to work yet. So right now we're developing these online databases that are managed in real time, and they include all the primary users. They actively maintain it. The regulatory agencies like the FCC or Ofcom in England or whatnot. So they also maintain these online databases. The SUs must periodically check an AFC database in order to be able to continue operating. So if you're, this sounds kind of cool. You can see this in Wi-Fi 6E in the 6 gigahertz band. This has some incumbent users, some primary users, but if done right with this AFC, we're hoping that Wi-Fi can coexist in this and actually operate at higher powers than we normally would be able to, right? To be able to extend our range from indoors to outdoors and whatnot. So here's a diagram from the Open AFC committee. I think there's a link down there, and consortium actually. So you've got updates, and there's a computation engine here, but these nodes now these Wi-Fi access points need to be communicating with the system, right? So, all right, here's another application, is decoding low density parity check codes, these LDPCs, right? I mentioned this in the 5G lecture. These codes approach the Shannon limit and are generally superior to other codes. All right, so there's a few in this family: turbo codes and polar codes and that type of thing. But speaking generally here, there's a family of codes that are very, 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 very good and close to being optimal. These are typically decoded iteratively, right? So you kind of iterate back and forth to actually decide what is the right code word that was transmitted. And that can be very computationally intensive, right? So some approximate approaches involve belief propagation. So it's a whole topic of AI, and this can be used to solve these things, right? So the belief propagation involves inference on a graph. I think Judah Pearl was kind of the guy that really developed this concept of trying to establish how you can show causality in systems, right? So and so there's we think about our Viterbi algorithm that we study, and will likely show up in some form on the final. So that's essentially doing inference on a graph, right? That Viterbi, that trellis that we're working with, that's a graph from a mathematical or computer science type of concept, right? So neural belief propagation uses recurrent neural networks to perform some of these required iterations. I know tons of hand waving here, but just trying to give you some exposure to this, right? So it's here. One of the cool things about this is that normally in machine learning applications, it's really expensive to generate or gather a lot of data and then label it, right? So if you're working with, let's say, an autonomous driving type application and the computer vision, and you're trying to recognize stoplights and stop signs, speed limit signs, pedestrians, bicyclists, other cars, other trucks, trying to figure out, how to perceive the environment, what's going on around you, so you can make appropriate driving decisions, right? So now you need lots of different images of pedestrians and bicyclists and signs and stoplights and road markings and that type of thing. And then someone's got to go through and say, draw kind of a box around a pedestrian and say, that's a pedestrian. And draw a box around a bicyclist and say, that's a bicyclist. And that approach is very, very, very costly and time consuming, right? So here, if we're trying to generate a data set, well, we can just go through and generate a bunch of random data, right? You guys have done this. And you learned how to generate some random data, then and save that data so you know what the correct inputs were. You can run them through your LDPC, code, and then to encode it, and then the answer, right? Because you created the inputs in a particular way, so you know what the results are supposed to be by the time you now actually decode it. So you can generate tons of these things, right? And then train this neural belief propagation system based on all of that. All right, so a lot of these papers here are kind of in the 2017 and later time frame. This dynamic spectrum access goes back to the very early 2000s. I know I was publishing papers in 2005 on this topics, right? So, but these are generally newer, right? So there might be some old papers you can find, but a lot of active research in this area. So what about equalization without this channel state information? So normally channel equalization, we just barely touched on this, right? So we did one lecture on receiver equalization, and we talked about zero forcing and maybe minimum mean squared error, MMSE type of things, and all. And then I think you ran some MATLAB example scripts on a decision feedback equalizer, right? So all of these things rely a little bit on channel state information, right? So, we could do a maximum likelihood approach where we do an exhaustive search over trying to figure out what the right result is, right, when we're receiving some symbols. But that's tedious, expensive to do, right? So we do these equalization approaches, and but they require this channel state information, right? So we send these reference signals or pilot tones of a known value and phase, known amplitude and phase, and at known times and known frequency locations or whatever, and then these things measure those and then converge upon this equalization. And so all this is part of this channel state, or CSI, channel state information. But all that adds a lot of overhead that we are not using to actually communicate data. MIMO drastically complicates this. And again, a little bit of hand waving here, but now you've got this H matrix, right? Where H is describing your channel, but instead of just a scalar value from a single antenna, transmit antenna, to a single receive antenna, it's now every combination of transmit and receive, right? So it's getting much more complex. So we can use neural networks, but it requires mapping of the radio signal processing to machine learning architectures, right? So you've got to figure out now, what are my inputs in this radio signal, especially when we're trying to do this MIMO type of system. What are my inputs? What are my outputs? And what kind of network should I use to actually solve this? But there's a number of papers working on this area right here, especially in MIMO and OFDM type of waveforms. Right, so then there's also modulation characterization. There's been some research solicitations that I've seen on this topic over the, maybe they're a couple of years old at this point, but modern systems adapt their modulation to current channel conditions, right? So you might measure the signal noise ratio and choose the size of the constellation, or the M area size of your constellation, depending upon that measured signal noise or signal interference noise ratio, right? But that again requires some signaling between the radios to communicate these decisions. So what about using machine learning to determine whatever modulation the transmitter is using, and all the different parameters, and try to learn that at the receiver, and just go and start decoding it, right? So that might reduce a lot of the signaling overhead potentially, and it's also going to have some applications in electronic warfare where you might be wanting to intelligently jam another signal by mimicking its modulation characteristics instead of just brute force jamming it. And then we also have some beamforming applications. We're just about done here. Just 2 more slides here. So we talked a little bit about millimeter wave systems and 5G. These would be things up in the 20 gigahertz and up range type of thing, right? So broadly speaking. So there we have just really difficult propagation conditions. These signals can be really attenuated just by walls and that type of thing. And it's also really hard to generate in an efficient manner RF power and amplifier signals without introducing a lot of distortion and that type of thing. So these guys are really hard. So we use beamforming with multiple antennas to try to concentrate that wave energy out there in that free space to maximize our effective radiated power. So, but to do this, we need to determine the location of the radios we're trying to communicate with. We might also want to be steering our signals away from interferers, right? Remember, antennas are reciprocal, right? So if our receive antenna has a certain directivity to it, I'm sorry, our transmit antenna is pointing in a certain direction, we can also do the same thing on the receive side and steer our beam, our focused energy towards the transmitter, and we will get some gain that way also. But we can actually steer a null, we can place a null in our antenna pattern in the direction of an interferer to try to reduce the signal from the interferer that actually gets into our amplification chain. All right, so I know that's a lot about antenna theory, but that's the general concept is we're trying to focus our things, but that's really hard, right? So we need to solve the amplitude and phase coefficients for each antenna elements in real time because things move. They're moving, right? So we need to update this. So it needs to be at least in near real time, accounting for all sorts of non-idealities like mutual coupling. If you put one antenna element next to another, it's going to affect it, right? And we call that mutual coupling. So its radiated field is not going to be like you would calculate it using a simple equation. Right, it's going to be kind of affected by it, right? So there's lots of non-idealities that you have to account for. So this beamforming sounds cool, but it's super hard to implement in practice. So here's some, a paper here that you can download. Some machine learning applications in millimeter wave beamforming. So some different applications here on how do you implement it and that type of thing. So all right, I will so I know that's a lot, and I will in an updated final exam preview, once I've written the final exam, I will kind of steer you and helping you to understand exactly what you need to be accountable for in both the recorded lecture that I do expect you to watch, listen to, that's the standards and research trends, and then also this lecture today. I know we covered an enormous amount of material, so but I do want to be able to assess you on a little bit of that. All right. I will, again, not be available tomorrow, but check my online calendar or to make appointments or shoot me an email and we'll figure out when we can meet. Get your late assignments in. Otherwise, have a great week.